Ladies and gentlemen, your class recording has started. So, first, probably gonna sound pretty bad on the recording. All right. Yesterday we started talking about phase changes and things changing state. Phase change, change of state, same thing. Just a different way of saying the same thing. This stems out of our discussion about kinetic theory from last week. So we talked about kinetic theory that we use to explain states of matter. First, the fact that it's a kinetic theory would tell us two things, right? What are the two things the fact that it's kinetic theory tells us? Andy, go ahead.
Why it happens.
That's the theory part, right? Why it happens. And the kinetic part tells us that it deals with motion, right? And we got into the discussion a little bit more, and we said that it doesn't only deal with motion, it also deals with another factor too. And what's that other factor?
Energy.
Energy deals more with is more of a relation of motion. Okay? So it deals with motion, but we also said that if we want to take into account attraction, how strongly are those particles attracted to one another? And if we consider both of those factors, we can determine what state of matter something will be in. For this discussion, if we want to talk about something changing states from one state to another, we also have to consider those two factors and what we have to do to the motion of the particles and the attraction between those particles that allows us to transfer from one state to another. First, gave you the triangle, right? The 6 different states or phase changes that occur. We said that all phase changes, regardless of which one of these 6 there we're talking about, are reversible physical changes, right? That the composition of the substance is going to remain the same, but there will be significant energy changes. So there are changes to the properties of that material, but not necessarily to its composition. We talked yesterday about this change of state, right? There we go. And so when something melts, what happens? It goes from a what to a what? A solid to a liquid. And Lorna, what has to happen to the energy of the particles when something goes from a solid to a liquid? The attractions decrease and the movement increases, right? So those two things have to occur. In order for that to happen, right, from an energy standpoint, what do we have to do?
Add energy.
Add energy, and that makes melting what kind of a process? If we're putting energy into it, it is a endothermic process, right? So if we're melting specifically, excuse me, that's when something goes from a solid to a liquid. Particles become less ordered. They move more. And that requires energy to be added, so that's an endothermic process. And I think at the end of class yesterday, we talked about that any of these processes that involve adding energy are going to be endothermic processes. When something goes from a solid to a liquid, we call it melting. When something goes from a liquid to a gas, we call it vaporization. And when something goes from a solid to a gas, we call it sublimation. Notice the arrows on my drawing, not on yours, it's not in color, but on my drawing, right? All of those arrows of those 3 phase changes are all red. Why? Because we have to add energy. We have to heat it up to make those things happen. Good there? All right, let's go the other way. Freezing. I'm thinking probably most of you are aware that when something freezes, what kind of phase change are we talking about? It goes from what to what? When something freezes, it goes from a liquid to a solid, right? When something goes from a liquid to a solid, what has to happen to those 2 factors that we talked about in kinetic theory? What has to happen to those 2 factors if something goes from a liquid to a solid? Lauren?
Attraction increases.
Attractions are going to increase and motion is going to decrease, right? So, particles become more ordered. The average energy decreases and the particles move more slowly. That allows those particles to attract each other more, and it becomes more ordered. Remember we said that solids have that nice orderly arrangement of particles, right? A nice regular pattern. In order for that to happen, energy has to decrease, attractions have to increase. start to attract each other more or hold on to each other more, and they move less freely. So we're decreasing movement, we're increasing attraction. In order to decrease movement, the energy of that substance needs to decrease. But conservation tells us that if the energy of one substance has to decrease, what has to happen to the energy of another substance? It has to increase, right? So these materials that are freezing will actually give off heat. I know that seems a little counterintuitive, but they will give off heat to make themselves colder. And because they are releasing heat into the surroundings around it, we refer to those as exothermic reactions, which is back on the front page. I think it's letter C of your outline, if I remember correctly, underneath Roman numeral number 2. Right? Exothermic means that energy is blank to the surroundings. What do we have to do to make something exothermic? Release, right? Energy is released into the surroundings from the substance. Okay, good there. Other exothermic changes are other changes when a substance needs to decrease in energy, when particles need to become more ordered and attract each other more. So when something goes from a gas to a liquid, like it says up on the board, we refer to that as condensation. Okay? When something goes from a gas directly to a solid, we call that deposition. These things happen not as frequently as things go from gases to liquids to solids, right? But those things happen, right? One example that most of you are probably familiar with is dry ice, yes? Okay. You know what dry ice is? Dry ice is solid carbon dioxide, but it goes directly from a solid into a gas phase. So if you put it out on the table, you'll see it kind of like vaporizing off of itself, right? But the table doesn't get wet because it doesn't go through that liquid phase. It goes straight from a gas phase or a solid phase into a gas phase. Same thing when it cools down. If you get it cold enough, carbon dioxide doesn't go through a liquid phase. It'll go straight from a gas phase into a solid phase if it's cold enough. Okay. All right, good there. Because we're talking about these phase changes, sometimes we want to monitor the temperature, right? And that's what you did in your lab. So I'm going to jump ahead for a second and look at the picture, then we'll fill in the blanks after we talk about the picture. Okay? All right, up on the board is the same picture you guys have in your outline. It says heating curve for water. On the two axes of this graph, right? Temperature on the y-axis, heat added on the x-axis. Heat added, heat is a specific kind of what? Energy, right? So this graph is showing the relationship between temperature and energy. Because it's water, I think most of you will probably be able to interpret the diagram pretty well. So here, this graph starts on the y-axis at minus 20 degrees Celsius. What state of matter does water exist in at minus 20 degrees Celsius? It's what?
Solid.
It's a solid, right? It's ice. So, during this section of the graph, right, the x values are increasing, right? We're moving to the right on the graph. And the y values are also increasing. Yes, they're negative, but they're getting higher. So this is ice warming up. But then, we see this section right through here. First, the temperature where this occurs is what on the Celsius scale?
0.
0. And most of us, I think, are probably familiar with 0 on the Celsius scale is the temperature where ice does what? Ice melts, right? But water will freeze. Same temperature, okay? But during this section of the graph, the x values are increasing, right? Because we continue to move to the right. But what's happening to the y values? They're staying the same. So is the temperature changing during this section? It is not, but we are still adding energy. Okay? Once we pass this point, during this section of the graph right here, again, x values are increasing because we're continuing to move along the x-axis, but then again, y values start increasing. This section of the graph starts at 0 on the y-axis, and it goes to 100 on the y-axis. This is water in what state of matter? That's a liquid phase, right? 0 is where water freezes. 100 degrees Celsius is where water does what?
Boils.
Boils, okay? Once we get to 100 though, right, again, we see on the graph that this graph is horizontal, meaning we keep adding energy to it, but it's not getting any hotter. The temperature is remaining constant until this point, and then it goes up again, right? Above 100 degrees Celsius, water is existing in what state of matter? Gas phase, right? So it's steam now. Okay? All right. Those of you that have made your graph for the lauric acid have seen something similar to this curve, but in reverse. And if you just remember what the lab quest looked like, okay, I'm going to draw a sketch up here. The temperatures aren't exactly right. The temperatures aren't correct, but your lauric acid graph probably looked something like this. It went down and went down and went down, and then it went flattened out. Okay? And then it went down again and maybe flattened out again, and then we went down again and flattened out again, something like that. Okay? When you got your lauric acid, what state of matter was it in? In the test tube, what state of matter was that lauric acid in? It was a liquid, right? And if you watched it, it remained a liquid for the first 10, 12 minutes, something like that. And then the temperature flattened out. And if you were looking at your test tube at that time, you would start seeing what was happening to the lauric acid in our test tube. It was freezing. It was turning into a solid. Even though it may not have been cold, or what we think of as cold, it was still freezing. That's what we call it when something goes from a liquid to a solid. But the temperature was not changing. It remained steady until it froze all the way and you put it in the cold water, right? And then it went down and got cold again. Now here, was this another phase change? Did it go from solid to Bose-Einstein condensate? No. These flat lines on the graph, while this one represents a phase change, these flat lines on the graph, you might have two, you might have one, depending on how long you took your data, don't relate to other phase changes. They just relate to the solid getting to the same temperature as the water that it was sitting in or the ice bath that it was sitting in, right? It cools down, but it's only going to cool down to the point where it gets to the same temperature as the ice, and it won't get any colder, because ice can't make it any colder than that. Okay? Does that make sense? All right. Why? So, last Thursday, when we were using the analogy of you guys at school to represent the states of matter, right now, you're representing what state of matter? Solid, right? Small amount of movement, ordered position, et cetera, et cetera, et cetera. And we said when the bell rings, you're going to go and represent what state of matter? Liquid in the hallway. But when the bell rings, do you get up and immediately go out into the hallway? No. You stand up out of your chair. You get your backpack. You put your folder or your binder back in your backpack. You take your pencil, you put it into your backpack, you zip it back up, put your backpack on, then you go, right? There's a transition phase that you have to go through. You can't go directly from being a solid to being a liquid. There's things you got to do first. If we're talking about particles in a substance, particles in a solid are very attracted to one another. But in a liquid, they're not so attracted to one another. So we have to sort of separate them all out in order to allow them to move faster. while you are getting ready to go out into the hallway, you are moving, right? You're packing your backpack, you're doing some things, okay? But you're not, and this is going to look good on the recording, right? But you're not moving. Does that make sense? Right? You're moving, but you're not moving. Right? Moving represents temperature. That's what the temperature tells you. How fast do those particles literally move from one place to another? But the energy of those particles can increase even without an actual movement. And that's the getting ready part, right? When you go from liquid hallway to gas phase gym class, right? You don't go straight from the hallway to gym, right? What do you have to do? You go to the locker room, you get changed, you put your backpack in the locker room, right, and get ready for gym class. Same thing, there's a transition there. Right? And that's what those particles have to do. Even though we're adding energy to them, they may not actually be going faster. So, during phase change, temperature of a substance does not change during the phase change. The energy that we may be adding, or that we're adding in that situation, goes to ordering or disordering the attractions between the particles, right? It's getting ready to change from one phase state to another, right? Letter B, the energy goes to making or breaking of attractions, right? Or orderliness of those particles. Oh. Good there? All right, so going back to the heating diagram, right? This is water sitting in class. This right here is water packing up its backpack and getting ready to go out in the hallway, right? It's getting ready to go. This is water in the hallway, right? This is water getting changed for gym class, right? This is water in gym class, right? There's that transition period to go from one state to another. Good there? Tomorrow, we will look at the phase diagram and see how the temperature and the pressure that an object or that a substance is under can affect that state of matter and how easy it is to change from one to the other.